Hello, this is the last part of our concurrent computing discussion. In this last part, we discuss three other systems, each of which has its own pros and cons. But these systems are popular or unique. The first one is Java thread. The second one is Ada thread. The third one is Pthreads. So, because everyone in this class has learned Java some time ago, therefore our discussion would only focus on the thread components. Java has two ways to create threads. The first one is create a new class derived from the thread class and overrides the run method. This is very similar to what you are used to with thread method. The second one is you define a class that implements the runnable interface. So let's take a look at a very simple example. Method one uses the thread class. So here we have the thread class provided by Java. And here we extend the thread class to yield a new thread class called hello thread. And then we override the run method. So in the run method, we only printed out one line, hello world. So the main program create a new hello thread, which is a derived class of the thread class. And this is referred to as the T. So to run this thread T, we call the start method of T. So here we create a hello thread and T here, and then we call the start method. So when the start method is called, then this thread will run, print it out, hello world, and then finishes. So this is very simple. To use the runnable interface is also very simple. It's a public interface, runnable, and then inside the runnable interface, we have a public abstract void run. So you simply override or design a new run method, and you are done. So let's take a look at a simple example. Here I have a class A that has a name, and the argument string is used to initialize the name of the class A. And we have a method setName to change the name, and we have a getName to return the name of this class here. And then we declare a second class AA. This AA class extends A and implements a runnable. So in this AA class, we still have AA's name and the name, and then we override this run method. So this run method iterates 10 times. For each iteration, it gets name, which is the name initialized, and then print out hello world. So this is so simple. Now the main program, we create an AA class, giving it a string Romeo. So we use Romeo to initialize AA here. Then this is referred to as the F1. So this F1 thread is initialized by Romeo. And then we create a new thread F1. So this is a thread T1, and run it. We do the same. We created another AA, we call it F2, initialized by Juliet, and then create a thread with the new thread method, giving it F2, and returned the thread classes T2, and then we run T2. Therefore, up to here, we have two threads running, T1 and T2. T1 is initialized by Romeo. T2 is initialized by Juliet. These two threads would run concurrently. So which one will print prior to which one, we don't know, because that depends on the system. But anyway, T1 would iterate 10 times. Every time it prints out Romeo, followed by colon, followed by hello world. T2 does the same, except that the name is Juliet. So we have 10 lines of Romeo, hello world. We have 10 lines of Juliet, colon, hello world. The mixture of these two 20 lines would depend on the system. So we may see 2 lines of Romeo, hello world, followed by 1 line of Juliet, hello world, and so on and so forth. As we mentioned throughout the whole semester, multi-thread and multi-process behavior is dynamic. We have no way to predict which will happen before something or after something. Now let's take a look at a more interesting example. Let's compute a Fibonacci sequence. This time, we use the Fibonacci class as an extension of the thread class. Therefore, we're going to override the thread classes, the run method. So we have the results and the input n, and we have a public function Fibonacci. This is basically in C++ wording is a constructor. So we use the input argument n to initialize this class's n. So the run method goes as follows. If the input value here is 0 or 1, we return 1 because the first two Fibonacci numbers are 1 and 1. If n, assuming that n is larger than or greater than 0, then if we are here, the value of n is larger than or equal to 2. So we create a Fibonacci class, we call it n minus 1. So this created thread is called F1. Then by the same procedure, we created thread F2. Now we have 2 threads created. We run them, F1.start and F2.start. So both threads start running. F1 computes n minus 1. That is the n minus 1th Fibonacci number. F2 computes the n minus 2 Fibonacci number. So we need to join them in order to get the results from F1 and F2. So Java provides the join method. So F1.join, meaning waiting for F1 to complete. F2 join means waiting for F2 to complete. This join method is usually in a try-catch block. That is interrupted exception. So basically, after creating 2 threads and running them, we are here waiting for both threads to complete. Once both threads complete, we retrieve F1's results and F2's results and add them together and put into the results of this class variable. So get results simply returns the value of the results of that particular class. So this is the run method. Now here is the main program. First of all, we need to create a Fibonacci class. This class, it takes the argument value from the command line when you run this program. So this value is used to create the Fibonacci thread class F1. Then we run it. So the main program, in order to get the results from F1, the main program must put this join in a try-catch block. So once the join completes, we have the result in this F1 class. So we just print it out. So this is very simple. You probably would not use this method to compute Fibonacci numbers, because this way is very, very inefficient. If you don't believe me, you just consider there's a recursion. We will return to this point if you are interested at the end of this lecture. Now, we know how to create thread, how to join thread. The first thing is the synchronized keyword. The synchronized keyword is actually an implementation of mutual exclusion so that a critical section can be implemented properly. Here, in this class, we synchronize. So in this class, we have a count, private variable. Every time we call inc, we try to add 1 to it. But we can only allow one thread to either increase or decrease this variable. Therefore, we add synchronize this class here and return the value. Now, keep this in mind when we talk about monitor. When the caller of this inc received return value, by the time the caller prints this value out, the printed out value may not be the current value of the count variable, because other thread could call inc or dec at the same time or in some sequence. Between you get this value and the time you print this value out. So very simple, synchronized is a way to build a critical section so that mutual exclusion can be implemented properly. The next step is lock. In thread manager, we use mutex lock. But in Java, it's referred to as reentrant lock. Why we use the word reentrant? You will note it here. So a lock, a reentrant lock is simply a lock. Only one thread at a time can acquire the lock, and all access to shared resource requires that lock be acquired first. In other words, if we have a shared resource, all thread that wants to use that shared resource must acquire the associated lock of that resource. Who can get it? We don't know. Only the one that acquires successfully the lock can use it. Of course, that thread must release the lock. So basically, a reentrant lock is just like a synchronized keyword. But in Java, the reentrant lock is something more. It's referred to as a acquisition count. What does that mean? This is the term reentrant. So a lock holder can acquire the same lock again and again. Always keep this in mind. A lock has an ownership. Only when a thread successfully acquired a lock, then that lock has an owner. That is the lock, the thread that successfully receive the lock. Any other thread, as long as it's not the owner of the lock, cannot release that lock. So the reentrant lock allows the lock owner to lock the lock again, which is something in this course we do not recommend you to do as a beginner. So the acquisition count initially is 0 if no one locks the lock. Now, if thread A successfully acquired the lock, the acquisition count is increased by 1. If thread A acquires the lock again, the acquisition count becomes 2, and so on. So when the owner of lock releases the lock, the acquisition count is reduced by 1. Just like a thread manager, we use lock to acquire a lock and unlock to release a lock. So if you are a beginner, I strongly encourage you do not recursively lock a lock. Always remember, if you lock the lock in a reentrant way n times, then you need to unlock it n times so that the acquisition count becomes 0. As a result, other thread would have a chance to lock it. Otherwise, if the acquisition count is non-zero, no other thread can get it, even though you are not using it. So here's an example. We declare a reentrant lock. We call it MyLock. So the locking part is easy. You just call MyLock.lock. Then in your unlock, put in a try, and finally block. So this is very simple. Then it's Java's monitor. Java does not have an explicit monitor concept. So if you like monitor, you have to build by yourself. So the monitor in Java is an object. This object has a lock shared by all threads that wants to use this common object. So this is usually implemented by synchronized keyword. A thread wants to use this common object. First of all, must acquire the lock associated with that object. This is the mutual exclusion boundary of a monitor. After using that common object, a thread must release the object. That's exit the synchronized block. So this common object, which is usually a class, you may consider it as a monitor. Remember when we talk about monitor, we said the concept was first created by Per Brinch-Hansen. He called that class as a shared class. That's the beginning of the monitor. Then, in the classical way, a thread inside a monitor or executing inside a shared object, sometimes it cannot continue because that thread may want to wait for something to happen. In classical way, we execute the wait method. When someone makes that event happen, that someone execute notify in Java or signal in classical monitor to release a thread. So let's discuss Java's waits first. First of all, you have to remember wait must be executed inside a common object, just like the monitor wait must be executed inside the monitor. So Java uses wait to wait on an event. Java uses notify to release a thread and the notify all method to release all waiting thread. So either way, the caller of notify or notify all simply indicates to one or all waiting thread on that event that the event you are waiting has happened. So basically, Java does not have the condition variable type, and the programmer must simulate an event. By the way, finally, you have to be very careful. In this class, we always emphasize the monitor of for type, but Java uses the Mesa type monitor. We will return to this point soon. Now, when a thread inside a shared common object, the call to wait causes the caller to release the lock. Which lock? The lock associated with the common object. So that means a thread enters a common object by acquiring the corresponding lock. And if the thread wants to wait for something, to wait an event to happen, that thread call waits. No matter what, when you call waits, the thread must release the lock implicitly. So when a thread calls wait, that thread would not be the owner of that lock. So wait should always be wrapped in a try block because it throws interrupted exception. So as we mentioned earlier, wait can only be invoked by the thread that owns the lock on the object. That is the monitor. The thread that calls wait becomes waiting until it's notified. Waiting where? Is it waiting? We don't know, we don't care. But in classical monitor, when you call a wait, that wait is related to or attached to a condition variable. So in classical monitor, when you call wait, you are blocked and put into the waiting list of the corresponding condition variable. But here we do not have a condition variable, and hence we don't know where the caller of wait will wait, but that doesn't matter. So a release thread from wait, that is due to notify or notify all, a thread is released from its waiting state, becomes inactive until it can reacquire the needed lock. Remember this, let's say thread A acquired the lock of the common object, and somehow thread A calls wait. Thread A would be blocked immediately, and the lock acquired by thread A will be taken away. So thread A is no more the owner of the common object lock. And thread A is in the waiting state. And then later on, thread A is released because of someone called notify or notify all. Thread A is released from the wait. Where does thread A would wait? We don't know. We just assume that thread A could be waiting outside. So in this case, thread A becomes inactive until thread A can get the lock of the common object back. Once thread A gets the lock back, that is, thread A becomes the owner of the common object. It's active, running inside the common object. So this explanation is a bit messy, a bit more complex than classical monitor, but it's still the same. Caller to wait blocks. When the caller is released, it would be inactive until the caller could get the lock back. When? We don't know. When the caller gets locked back, the caller resumes its execution inside the common object. Now, a thread calls notify to release a waiting thread. If a thread calls notify all, it's to release all waiting threads. Whether this thread calls notify or notify all, after calling either one, the thread continues its execution. Now it tells you something. Java uses the meta type. Remember, under for type, the caller to signal would yield the monitor to the released one, right? Under Mesa monitor, the caller to the signal method continue, but the released one will be put outside of the monitor or wait somewhere. So always remember, Java uses the Mesa type monitor. So the release thread becomes inactive, as we mentioned earlier, and wait until the object's lock will become available. Whether an inactive thread can acquire the lock again immediately is determined by the lock mechanism. For example, A is blocked because A called the wait method, and thread B calls notify to release thread A. Now remember this because Java uses the Mesa type. Thread B, the caller to notify, continues. Thread A is released from the waiting state and put somewhere. So upon exit, thread B, who called notify earlier, would release the lock so that the lock is available. Can thread A get lock back? We don't know. There's no assumption that A would get the lock back immediately. So to avoid this situation, a good suggestion to you is use notify and notify all as the last statement, because it can avoid many potential problems. Why? Because when you call notify or notify all, if it's not the last statement, the caller of notify or notify all still owns the lock of the common object. So it may interfere some other inactive thread. But if the caller to notify or notify all is the last executable statement and gone, well, that's fine, because the interference between the caller to this and those inactive threads will be minimal. Now let's take a look at a very simple example. I called it bounded counter. We have a counter. This counter is bounded. What does that mean by bounded? Its value must be between the minimum value and the maximum value. Here, we only show you the minimum. The maximum you can declare similarly to save space so that I could put a complete class on a single slice. And then, see, we put synchronize here. That is when this method is running, no one can enter. So when one of these methods is running, it's the only method of this class running until it ends. So we have a counter implement bounded counter. Okay, so the method value simply return the count here. Count is initialized to the minimum value. the increment value, the increment method, first of all, wait for some time, and then shift the counter to its new value. That is the current value plus 1. This await INC, the await to increase the value. What does that mean? If the current value is at the maximum, you cannot increase it because, as we mentioned earlier, the counter has a bounded value between minimum and the maximum. So if you wish to increase the value by 1, and if the current value is already at its maximum, you have to wait until its value is reduced to below the maximum. Once it's less than maximum, then you can increase. The decrement is simple. Wait for something. That is, if the current value is already at the minimum, you cannot decrease the value. So we wait until the current value is not minimum, or at least larger than minimum. Then we decrease the value of the count. Then we have set count. We use new value. We put new value into variable count and release everyone waiting. So by calling notify all, then everyone waiting will be released. This thread could be waiting for the value being larger than minimum, or waiting for the value being less than maximum. We simply release all, giving everyone a chance to do their job. So for await inc, we test to see whether the current value of count is greater than or equal to the maximum. Should that happen, you cannot increase. So we wait. Always remember, wait must be in the try catch block. So if this thread is released, it would come back and try to get the lock of the this counter class. The lock is implemented by the synchronized keyword here. So by the same reason, await deck is the same. If the current value is less than or equal to the minimum, then we wait until it's larger than the minimum. So let me remind you, many beginners would believe, okay, I call value, then I get the internal value of the counter. Then you use the return value for further decision making, but that is very risky because this is multi-threaded environment. When you get return the value, somebody may have already changed the counter value. So your decision making may be wrong. So here we have a buffer. This is a bounded buffer. We implement the bounded buffer. So we have an array, we have an in pointer, out pointer, and a counter. This counter simply counts how many elements are there. So here we initialize the buffer. Then we have get count, return how many elements are there. This is a very, very risky move, as we mentioned several times in this lecture. A capacity return the buffer length. We will have put and get on the next slides. So put is synchronized. That is, put and get can only have one put or one copy of get could run at the same time. So if the buffer is full, then we wait. Then look at here, this is while statement. When I'm released, I have to go back, check it again. Because after I'm released, before I can get the lock back, somebody may have already filled empty slots. And this is something you have to remember. We discussed it in some length in the discussion of the monitor. So if I got the lock back and the count is less than length, so I could put the value in and the advanced in pointer and the test to see whether count plus plus is 0. Then we notify everyone who's waiting and ask them to come back and check to see whether you can run. Now, for the get, it's the same. If currently the buffer is empty, we wait until I'm released, because this is a Mesa monitor. We have to go back, check to see between the time I was released and the time I can get locked back. There could be somebody messing around, changing the value of count. If by the time I am back, the value of count is still 0, then I wait. If by the time I come back, count is not 0, of course, the buffer has something. Then I retrieve it and put north into the position, advance it, and after, and check to see whether count minus minus is equal to buffer length. That is before I retrieve the information. It was 4, then I notify everyone, return the value we retrieved here. So as you can see, in Java, we do not have the monitor concept. We do not have condition variable. So when we signal in a classical monitor, we know from where we could release a thread. But in Java, we don't have condition. Therefore, when you notify or notify all, that everyone waiting will be released. Now, the early version of Java doesn't have semaphore, but later Java version has semaphore. This file, java.utility concurrent semaphore, is a counting semaphore. To use the semaphore type, just import this file. Actually, Java supports concurrent computing in a set of files, that is java.utility.concurrent.start. You could include them all into your program if you wish to do so. So in a counting semaphore, the semaphore has an internal counter. We use counter throughout all previous lectures. But Java's semaphore refers this counter to as permits. You will see why we call it permits. There are 2 constructors. Semaphore with an argument, a permits. So this means we create a semaphore with initial value for the counter. And this semaphore is a non-fair one. Now, if you add a second Boolean argument true, it means the waiting list of the semaphore is going to be fair. That is first in, first out. So if you use this form, the semaphore is the same as what we have learned so far. And if you use this form, it's going to be a fair semaphore. First in, first out. Now, the semaphore class has several methods. We only mentioned a few. You could look up the semaphore document at Oracle's site to learn more. So in Java semaphore, the wait method in our discussion is acquired. But there's 2 acquired forms. If you call acquire without arguments and acquire with an integer argument. Now, if you call acquire, it's just like you call the wait method. So the call to the acquire method acquires a permit from the semaphore. That is, the permit will be subject by 1. The caller will be blocked until 1 is available, or the caller is interrupted. So you know the try catch will be used. Now, Java provides something we did not discuss. You could add, you want to acquire several permits. So acquire 2, it means you want to acquire 2 permits from the semaphore. You will be blocked until all permits are available. You get them all or nothing. If your request is available, then you get them all. If 1 is missing, then you wait. So this is the meaning. Blocking until all permits are available, or the caller is interrupted. As a result, acquire should always be wrapped in a try-catch interrupted exception block. But Java also has an uninterruptible form of the acquire method. They are similar to the conventional wait. So the original acquire can be appended by the word uninterruptibly. So acquire uninterruptibly, that's our wait. So you call it without an argument. It means you acquire a permit from this semaphore, blocking until 1 is available. So we don't care whether the caller is interrupted or not. You just wait until the permit is available. So the second form, acquire uninterruptibly with a number of permits. You just wait until all permits are available. We don't care about the interruption. So it's your choice to use the uninterruptible form or without this form. So for release, the signal, it also has 2 forms. Release without an argument releases a single permit. Returning that permit to the semaphore class. Or you could return multiple permits. So these are the very simple forms. Now let's take a look at a twisted form of dining philosopher problem. Remember, we have a round table, we have a plate of noodle, and we have 5 chairs, and we have 5 philosophers. Previously, we have a chopsticks between 2 philosophers. But now, let's modify the original form. We put all 5 chopsticks at the middle of the table. So when a philosopher wants to eat, the traditional form or the classical form, this philosopher raise his left hand, get his left one, and raise the right hand to get the right one. So if this philosopher could get 2, he can eat. Then only 3 remains. Obviously, asking a philosopher to get the chopsticks 1 by 1 is risky because this is not a deadlock-free version. Think about it, pretty easy. Therefore, we change to the following form. Remember, we also talk about a solution. A philosopher must acquire both chopsticks at the same time before he can eat, rather than 1 by 1. So how about this? Initially, we use a single semaphore here. The initial value would be 5. A philosopher always acquires 2 chopsticks, that is, acquires the semaphore with 2 permits, then we know there won't be any deadlock. Let's take a look at this. I just simplified the whole form. So a philosopher think and acquire 2 chopsticks at the same time. And then after that philosopher could get both chopsticks, he can eat. After eating, release both. And then come back for another round of thinking and waiting for the chopsticks 2 at the same time and release it. Now, because a philosopher must get both chopsticks at the same time, therefore, the hold and wait condition is violated. This solution is deadlock-free. So here we show you the Java form of acquiring multiple permits being useful. Hopefully, you are able to explore further. Now, if you are not interested in Fibonacci numbers computation, you could simply stop here. But I strongly encourage you to dig a little deeper because it's very interesting. Now, let's analyze how inefficient the method we use on slide 6 is. Let's say Fn be the nth Fibonacci number with F1 equals 1, F2 equals 1. Let's Tn be the number of additions to compute Fn. So the program on slide 6 computes Fn plus 1 using 2 threads. One thread computing Fn with Tn additions. And the second thread computes Fn minus 1 with Tn minus 1 additions. So the thread that used to compute Fn minus 1 would use this thread to compute Fn, which uses Tn additions. And it also uses thread to compute Fn minus 1, which uses n minus 1 additions. And then we add these 2 numbers together, we need 1 more additions. So to compute Fn minus n plus 1, the total number of addition will be Tn plus Tn minus 1 plus 1. If you have anything in doubt, please pause before continuing. Understand why we have this formula, even though on slide 6, the method is multi-threaded, but we are interested in how many additions the program would use. So whether your program is written in a sequential way, computing Fn first, followed by Fn minus 1, the total number of additions is still this. So the next step is, let's figure out what this number is. So actually, we have Tn equals Fn minus 1. Let's verify by some observation. F1 is this. And because when we compute F1, we don't need any addition. It does the same for T2. When we compute F3, we compute this one, we need this number of additions. We compute this one, we need this number of additions. And then we did 1 more, which is this one. So the number of additions is 1, which is F3 minus 1. So you can verify F4 and F5. But we can certainly prove it rigorously by the use of mathematical induction method. So the base classes for n equals 1 or equals 2, that's obvious because F1 and F2 are both 1s and T1 and T2 are 0. So the induction method, we assume that from 1 to n, this expression holds. Then we want to know whether this is still true. Now we want to know this, but we know Tn is equal to Fn minus 1, because we assume that from 1 to n, this expression is true. So Tn is this. Therefore, Tn plus 1 is equal to Tn plus Tn minus 1 plus 1. And that is the recursion formula. Then we replace Tn by this, replace this by this. After some simplification, we have this. Okay, so as you can see, the Fibonacci number increases rapidly. As a result, the number of additions to compute Fibonacci number using the method we mentioned would also increase rapidly. So in this way, we establish the fact that the number of addition to compute Fibonacci number, either you do it recursively or in a multi-thread way, as we mentioned, is closely related. It is very interesting to note that Fibonacci number can be computed directly rather than using the formula. The Fn plus 1 is equal to Fn plus n minus 1. So here is the way to do that. We don't prove it here. We define two numbers, phi and psi. Phi and psi are nearly identical, except that phi use plus, psi use minus. Then the nth Fibonacci number can be computed directly as follows. That is, phi raised to nth power minus psi raised to the nth power, divided by the square root of 5. After some manipulation, it can be simplified as follows. As phi raised to the nth power divided by square root of 5 plus 1 over 2. And this is referred to as the floor function. It's just a truncated value. So as you can see, Fn increases exponentially because phi is a constant. Now the variable n is here. Therefore, Fn is increased exponentially. Of course, Tn, the number of additions to compute Fibonacci number on slide 6 is also exponential. Therefore, using the way on slide 6 to compute Fibonacci numbers is very, very slow. This is the diagram showing to you from Fibonacci 1 to Fibonacci 40. Only F40. See, from F1, F2, the value is nearly flat. Then the curve starts to shoot up around 30, 31, and this increased exponentially. F40 is this value. So this tells you how inefficient the method on slide 6 is. I'm sure many of you knows how to compute a Fibonacci number in this way. Given a non-recursive but iterative, and 0, 1 return 1, otherwise we have 2 previous and this value. So we iterate n times. Every time we add the previous value and this value together to the result. Once the result is computed, we move this value to the previous one, the computed result to this one. So in n iterations, we have Fn. So in this case, every iteration we have 1 addition. Therefore, this method is order n. That is linear. Everybody probably knows this method. Given the formula, you will definitely come up with this method, right? Can we do better? As a computer science student, always try to make your program more efficient. Now, let's try. We certainly can do a whole lot better, but let's start with a simple problem. Given an x and n, how fast we can compute x raised to the nth power? Okay, now you know, we just execute loop. Every iteration we multiply x to the previous value, that's fine. But that algorithm is order n. Now let's think about this. Look at this xn. If n is 0, the value of x raised to the nth power is 1. If n is even, let's say n is equal to 2k. So x raised to the nth power is equal to x raised the square of x raised to the nth power, right? So in this case, given an n, we determine k, which is equal to n over 2. Then we compute this and then square it. Instantly, we cut the number of multiplications in half. Remember, divide and conquer. So what if n is odd? If n is odd, then n is equal to 2k plus 1. So this one, we factor x out. The remaining would be x raised to the 2k power. And x raised to 2k power is exactly this one, right? Therefore, the computation of x raised to nth power, if n is odd, then we figure out the value of k by dividing n by 2. Then compute this part. Once we get the result, we multiply x to it. Again, we also cut the number of multiplication by half. So this is the way we can do that. So let's take a look at this possible implementation. I assume that you are aware of C's bit manipulation. So we use a unsigned long. This is recursive power. So if n is 0, we return 1. So what does that mean by this? Remember, this AND operator is the bitwise AND. So what does that mean by this? This UL means unsigned long. So 0x01 means it is in hexadecimal 1, represented as a unsigned long. So that means on paper, this value is 0, 0, 0 followed by 1. The last bit is 1. If the value of n and this 1 n together, if we get 0, it means the last bit of n is not 1, which means n is an even number. In that case, we compute this. N shift to the right by 1 bit is equivalent to dividing n by 2. So this call to recursive power is compute x to the n divided by 2's power. The result would be return to 10, and then we square them. Now, if the value is 1, so we know we could compute n minus 1 as a power, which is even. We call x n minus 1 as an argument to recursive power. So this one, we cut the multiplication by half. The result is multiplied by x. Therefore, this, even though we use recursion, is still much faster if n is very large. Because of this, every time we shift the n to the right by 1 bit, it's equivalent to divide the n by 2. Therefore, it's this implementation is a log n complexity. Now, after knowing this, let's do Fibonacci number again. Please verify this formula. See, we have a 2 by 2 matrix 1, 1, 1, 0. Here we have n plus 1, fn, n minus 1. So fn minus 1 is equal to this one multiplied by this one plus this one by this one. So exactly the Fibonacci number. So fn is equal to 1 multiplied by fn, okay, and plus 0 by multiplied by fn minus 1. Okay, this is exactly the same. Fn equals to this n. So now fn minus 1 is computed by the same thing. So we could keep multiplying fn, n minus 1, fn minus 1, fn minus 2 together. We have this. Fn plus 1, fn is equal to left multiply f1, f0 by this matrix raised to the nth power. So basically, Fibonacci number computation is this. As long as we know how to compute this matrix power fast, we have a very fast computation for the Fibonacci number. But we know raising x to the nth power is of log n order. Of course, you can simply modify the previous implementation so that every time you are asked to compute a 2 by 2 matrix to the nth power, if n is even, then you cut it in half and so on. So using this formula to compute fn plus 1 and fn is log n order. Beautiful, right? So let's say, because in the previous method, we used not only additions, but also multiplications. Let's say every recursion, including the use of multiplication, requires 100-fold of the time of executing single addition. That is, all the instructions needed to execute one recursion, which include the system instruction to handle recursion and multiple multiplication, actually 8 and 4 additions. Let's say it's 100 times more. Now, let's plot, and this is log n curve, and this is order n curve. Somewhere around n equals 1100, log n, the value of log n is smaller than the linear. So this means if n is large enough, even though we use so many multiplications and additions in the recursive implementation, the log n algorithm is still faster than order n for n sufficiently large. You may want to say, you are crazy. We probably won't compute the 1100th Fibonacci number because it's already overflowed. Not sure you are aware of that. There is a GNU multi-precision package. You could compute an arbitrary numbers, addition, multiplication, and so on and so forth. That is the way people use to implement, say, cryptography algorithms. So, can we remove recursion? Yes, indeed we can. It's a bit tricky, but not so difficult. Again, we use binary. So suppose we want to compute x raised to the nth power. We first of all convert n to a binary string. Here, let's say 45 in decimal is equivalent to 101101. in binary. So x raised to the x 45th power is equal to x raised to the 101101's power. Now, let's start with this one. This is equivalent to 1 times 2 raised to the 0th power. The second digit is 0 times 2 raised to the first power. The third digit from the right is 1 times 2 squared. This one is equal to 1 times 2 raised to the third power. The leftmost one is equal to 1 times 2 raised to the 5th power. So this all add together, then we could cut them into these terms. The 2 raised to the 5th power, 2 raised to the 4th power, and so on. Now, because this one is multiplied by 0, so this is x to the 0th power, you get value 1. It doesn't matter in a multiplication. By the same reason, this 0, so x raised to the 0 would get us 1. Therefore, of these 6 digits, only 4 are needed. Do you see that? The 0 digits are not used because it would result in a 0th power, which results 1. Therefore, the binary representation of n in x raised to n provides selectors indicating which components should be included. 1 means yes, 0 means no. So this 1 here, 0's power is 1, so it's needed. And for first power is not needed. Let's trace it back because it has 0 bit here. So in this representation 101101, we need this one, 2 raised 0th power. We need this one, and this one. So after knowing this, we can do the power computation in an extremely efficient way. So we need to compute x raised to the 0th power, first power, the second power, the 4th power, 8th power. Why? This is 0th power. If it's 0, we have 1, it's first power, we have x. For the second bit is x squared, the third bit is x raised to the 4th power, and so on. So keep going. So now we need the value of n, the bit of n, running from right to left. We need the variable product to accumulate all of the needed power. So when a bit in n is 1, so when a bit in n is 1, we simply multiply the square of this guy and the previous accumulated product, multiply them together, we get new product. So what does that mean? As long as we scan the bit pattern of n, as we scan the bit pattern of n, no matter what, we square the current value of x. And if the current bit pattern is 1, we multiply the current square pattern, x, multiplied it with the current accumulated product, we get a new product. So after all bits of n are scanned, we have our results, right? If you have question, please refer to the previous slides. Look at how simple it is. So power initially is x. So as long as n is greater than 0, so we test to see the rightmost bit is 1. So if n and 1 equals 1, that means the rightmost bit of n is 1. Then we need it. So we multiply the current power to the currently accumulated results. And then we square the current power to become the power to be used in next iteration. Then we shift the bit pattern of n right by 1 bit. So isn't it very simple? This program requires some thinking to understand carefully. But there is an interesting question. Although most computers would not report integer overflow, but some could in the future. So if the current power is still good, but you square it, could call, when you square it to become the next power, integer overflow could happen. How do we deal with this? The solution is very simple, but it's your business to figure it out. So the worst case is n equals, or n has all 1 bits. So that means if we have we have n bits, then we have n iteration. Each iteration we square the power and multiply the current power to the product. Essentially, in this worst case, we need 2 multiplication per iteration. Because there are k bits in n, so the total number of multiplication is 2 times k. Now, because k is of order log 2n. Hope you understand this. So this algorithm is order n. It's much faster than the recursive implementation. So hope you enjoy this extra discussion. And this is the end of Java thread. Next time, we're going to talk about Ada, a very interesting language, but now it's not very popular, but very interesting. So see you next time. Goodbye.